made or lost, it can only be converted. We talk a little bit about what those conversions would do to heat, mechanical energy, etc. Energetically favorable reactions are usually those that give off a lot of energy. And so we're going to be coming back to that idea of energetically favorable when we talk about whether a chemical reaction in the body in biology can go, meaning go from the reactants to the products. And we ended here. Equilibrium is, this is a state of equilibrium in physics, and in biology the word equilibrium means it can do no more work. And this is where we ended in lecture, that if you are at equilibrium, you're essentially dead. And so no biological system is at equilibrium. This is a physical system, and so this becomes the basis of what we had started talking about both in lecture and in lab, that things move down their gradient towards equilibrium. And this is diffusion, which is a process that goes on throughout the whole universe. If you took a astronomy course, you find that the planets are actually going towards equilibrium, moving down their gradient from a concentrated mass and expanding outwards. Those are the things that physicists worry about. Obviously not in our lifetime, but there will come a time when everything has expanded to the point where it's not going to move anymore, and then the kind of questions that physicists ask is, does that mean the whole universe comes to a stop? So the idea of work is that it can produce change, and of course that's all that a living organism is about. One of the concerns, and the laws of thermodynamics are the staple of, Alexis, see me after class. The laws of thermodynamics is one of the staple laws of the entire universe. There's no doubt that it's true. And so one of the concerns that biologists had, we just got finished saying that things go towards equilibrium. If you were, you can think of order. What is ordered? And so this is a more ordered state to have the dicrystal all together in a pellet, etc. Once it goes to equilibrium, you can also consider this a state of disorder. And so what these laws of thermodynamics are saying is that everything naturally goes from a state of high order to a state of disorder. And then all of a sudden we're in a biology class and we're talking about life is all about being ordered. And this is, we have particular shapes. This is a very ordered shape. There's nothing random about that. We have plants and petals on flowers, etc. And so one of the questions that biologists had is it somehow possible that life would violate the basic laws of the universe, the basic laws of thermodynamics? And your book talks about it, but they don't use the names. And so they say no. One of the things that these laws of thermodynamics assumes is that you're in a so-called closed system. So you can think of the whole universe as a big box. And then everything that is the stars, the planets, the Earth is in that box. And so the laws of thermodynamics were first spelled out for a closed system. And so then we reach the question, since life is all about order, does that mean that we as living organisms violate the laws of thermodynamics? Your book says no, and the only reason that they give you is that we are an open system. And so what does an open system mean? It means that we exchange with the environment around us. And so, for example, we breathe in oxygen, which is coming from the environment into our bodies, and then we exhale carbon dioxide, which is coming from our bodies into the environment. And so because that classifies as an open system, that your book says, no, it's okay. We don't violate the laws of thermodynamics. For those of you who are going on in science, that kind of statement and question came out of a Nobel Prize winner. His name was Ilya Prigogine. He won the Nobel Prize in 1977, and without giving the reference to him, when your book says no, living organisms do not violate the laws of thermodynamics because they're open systems, they're really talking about his work. And so his work is called non-equilibrium thermodynamics. So we as a living organism, as an organism that has a order to us, and everything about our life is homeostatic, optimal range, etc., is under the category of non-equilibrium thermodynamics. So until we don't exist on this planet anymore, we're not going to just ooze out into the universe and become the puddle of dye that you see here. And so he wrote a book. Obviously, when he won the Nobel Prize, it was based on all the physics and the equations and the calculus and all that. But he wanted to disseminate his information to the public, and so he wrote a book called Order Out of Chaos. And Order Out of Chaos, if you've seen Jurassic Park, with the dinosaurs and the genetic engineering to make the dinosaurs, there was a statement in that movie about the butterfly effect. That if a butterfly flaps its wings, it has consequences as a chain reaction over the whole world. And so that is coming out of this book, Order Out of Chaos. And so what it means is that we are fighting, everything about biology is fighting equilibrium. We are fighting to stay in a state of disorder. Only when we no longer exist, when there's no longer, when we die, when there's no more chemical reactions, then we will follow the laws of thermodynamics and we'll go towards equilibrium. Our cells will no longer be ordered. If there's fluid, it will just run down its gradient. And so, so he was the one, Ilya Prigogine was the one that allowed us to make that exception. So he explained this so-called far from equilibrium physics. So we are part of far from equilibrium physics. But because we're a so-called open system, because we interact with the world around us, and the world around us, the universe around us, is the closed system, we don't violate the second law of thermodynamics. Okay, so I just wanted to, again, for people that are not, I know a lot of you are not in LAX, but if you're in LAX and you plan on going to science, this would be of more relevance to you. What do you want to, for people that are not, just remember that we don't violate the laws of thermodynamics. Okay, we do have to talk about free energy and metabolism. This is a so-called Gibbs equation. And this does relate to what we were talking about, or sometimes it's called Gibbs free energy equation. And the G here stands for the delta, the triangle stands for a delta, it means a change in free energy. And this stands for the, we can say the heat that's being released. This stands for temperature. The important term here is S. The one we want to concentrate is the term S. And S stands for entropy. And entropy essentially is a state, if you have high entropy, it relates to a state of disorder. And so it does, in fact, have some relationship to what we were just discussing. When something is at equilibrium, it is in a state of high entropy. It's in a state of high disorder. What does this have to do with biology? We're in the chapter called metabolism. We're talking about, we're defining metabolism as all the chemical reactions in the body. And part of what has to be considered is what will be a spontaneous reaction, what will be a probable reaction, and what will require energy inputs to make the reaction go. And so according to this Gibbs free energy, any chemical reaction that increases disorder, which is to say increases entropy, would be a probable reaction.
What's
And,
next? I'm sorry, what's next to the G?
What is what? Gibbs equation. Gibbs is the name of the person that worked out the equation. Again, lots of Nobel Prizes in thermodynamics. And so Gibbs is the name of the person. Sometimes instead of just calling it a Gibbs equation, it's called a Gibbs free energy equation. And so what he's considering is the free energy. You're deciding whether the free energy is going to require reaction is going to go with an input of energy or whether it's going to go without an input of energy. The bottom line, why this equation is of relevance, if you have a chemical equation that ends up on the product side increasing entropy, which is to say increasing disorder in the world, then you have a probable reaction. It does not require an input of energy. So it all comes back to that order disorder. The universe in general is increasing its entropy. It's increasing its state of disorder. And so this is why and what this is going to tap into is why we need ATP. We've already defined ATP as the energy molecule. If we didn't have this reality that we have to live under in terms of chemical reactions and entropy and S terms, we wouldn't need ATP, which gets back to the entire logic of this course, that we are not isolated individuals. We have to live interacting with the universe around us, which means that we have to follow the rules of the universe. So here are the terms related to that increased release of energy or an intake of energy. Here we have our reactants, and here's where we want to go. We started using those terms when we had the chemistry chapter. If you're on the left side of the arrow, you're on the reactant side, and now you want to make your product. So we usually want to go into this end of the reaction. So now the question is, if on the way from a reactant to a product, you are releasing energy, the energy usually, 9 times out of 10, will go out into the universe in the form of heat. Heat is a very disordered state of affairs. It's a form of energy that has a high degree of entropy. And so if this is what's happening, if you are releasing energy, then that whole situation gets a name. It's called an exergonic reaction. If you're exiting, you're going out. And so exergonic reactions in biology release energy. That means they're increasing disorder in the universe. And if you go back here, we had that picture of the bear. And so there are chemical reactions going on in the animal, and as a result of those chemical reactions, the body temperature is increasing, and then we have the adaptations to make sure the animal doesn't get too hot, one of which is to allow the heat dissipate, to thermoregulate and dissipate out into the universe, and so the heat is going out into the universe. This would be an example of an exergonic reaction. Exergonic reactions, in general, have, so the key is, let's do our equation again. And we have delta G equals, this is a term we won't even bother saying what it is, enthalpy, minus temperature, and delta S. Delta S is the change in entropy. And so if you have an exergonic reaction, if the chemical reaction is releasing energy out into the universe, then you are going to have a negative delta G. And so if you have, because you're increasing, this is just arithmetic. If you gave a number to this and you increase the number, then the minus sign would overpower everything else that's in that equation. And so if you have a negative delta G, that is a spontaneous reaction. And so these are the words you want to associate. Exergonic reactions are spontaneous reactions. They go, meaning they go from product side, from reactant side to product side with no energy input. Instead, they release a lot of energy output. So all of these terms, exergonic, energy is released, that means it's spontaneous, and delta G will be minus. That sign here is less than. If you have a sign in this direction, it means more than. And so that little, what's called a caret, that is so all of those terms put in your head or put in your notes together. Delta G means spontaneous. On the other hand, here we have the opposite sign of the coin. We have a reaction that we call endergonic. And so here, we are going from reactant to product. The products in this case are more ordered. And so once again, you have to think of entropy. If you're ordering something, you're turning something into a crystal, for example, that's a more ordered structure than if you just have sodium and chloride ions running around in water. And so that to increase order in the world, you have to put in energy. And so we're back to the fact that we are an ordered system. We are ordered organisms, and so we need energy. What's the energy going to be? It's going to be chemical energy for us. It's going to be ATP. In that case, it's a non-spontaneous reaction. The delta G sign would be plus or greater than 0. So all of these words you want to associate. Endergonic, energy required, non-spontaneous, delta G plus, and energy input in the form of ATP. So just make the list in your notes. Now's the time to take decent notes. Everybody have it? Everybody have this? All the words that are associated with this? Huh?
We go back to the other one,
Which one?
the one that we were on just now.
This one?
Yeah.
The book is introducing the topic to essentially explain why we need ATP. We started out this whole lecture saying that life is about order. Order, by definition, is a non-spontaneous reaction. In order to keep our bodies at order, in order to have reactions go from the left side to the right side, to create more order. This would be, for example, taking glucose and making starch out of it. If we were a plant, or making glycogen out of it, if we were in our own muscles. So that's a more ordered state. You need energy in order to make those bonds. So we cannot violate the rules of the universe, and so this is what all of this is about. It's essentially an explanation. The problem is most students don't ask any questions. You just take the information, you copy it down, you memorize it, but this is for people that think about why things happen, and so this is the answer as to why we need these considerations, because we cannot violate the laws of thermodynamics. Okay, so in order to make our world go, we are ordered. We're going to engage in a lot of endergonic reactions, which create more order, which are not spontaneous. And so our energy input is going to be that chemical molecule that we call ATP, our energy molecule. The other side of the coin is, what else do we need? If you've taken a chemistry course, or if you are taking a chemistry course, in a chemistry lab, the typical way to make a reaction go and put in energy, what do? Common way in a chemistry lab to get a reaction to start. You turn on the Bunsen burner and you apply heat. And usually the greater the heat, the faster the reaction goes. We have a limitation. Our bodies are at 37 degrees centigrade, 98.6 degrees Fahrenheit. We can't jack our temperatures up. If we were to force all our chemical reactions to go at that temperature, we would probably be 100 years old before we got most of them going. And so that's the importance of enzymes. Now, we had defined an enzyme previously, I think, by just saying it was a catalyst. And we defined a catalyst as saying it increases the rate of reaction. And once again, for students of biology, you want to get to the nitty-gritty. What does that mean to increase the rate of reaction? And And so here is our ATP molecule. The bottom line for ATP, why it's for the energy molecule, what we're tapping into, this is, we're going to start using the terminology that we use when we talk about chemistry. Look at all these negative charges. They're extra, they're hanging around. This is a very unhappy molecule. It doesn't like to be fighting with all those negative charges. And it's actually that property of ATP that is miserable, that it wants to get rid of the extra charges. That's why it's the energy molecule. And so if we look here, let me just go to this. This is why ATP is important, and then we'll come back to the enzymes. This is where we want to go. Here we are. This is in your book. This is, you're going to make now the amino acid glutamine. So you're starting out with one amino acid, glutamic acid. In order to make glutamine, you have to have what's NH3? Ammonia. And with the proper help of enzymes that we're not going to discuss right now, you can make the other amino acid that you need in your body called glutamine. This is a plus sign. So this is telling you that this reaction is not spontaneous. Excuse me, where's the plus sign? That this reaction is not spontaneous. It won't go on its own. So we can't just go from here to here. We can't just take an ammonia molecule, tack it on to an covalent bond to the glutamine amino acid, and create this, because it is non-spontaneous. So we have to use ATP. So what's going to happen is you're going to start with this molecule. You're going to have plenty of ATP that the mitochondria just made, and that's going to be available to the body. And the ATP is going to bind, one of the phosphates of the ATP is going to bind to the glutamic acid. In reality, what you've done is make the glutamic acid now just as miserable as the ATP was. The ATP is now actually happier because you got rid of one of those phosphates with all those negative charges. But now you've tacked on the negative charge to the glutamic acid, and you've made it unhappy. So unhappy is another word where you've raised up the energy state of that glutamic acid, which is to say you've made it more probable that the glutamic acid would undergo a chemical reaction with some other molecule. Why is that more probable? Because we started the semester, all the discussion in chemistry, we started by saying that electrons and atoms are very lazy. They don't like to be in a high energy state. They want to be at the lowest energy state possible. So that when you transfer a phosphate from ATP onto another molecule, you have to push that molecule up in its energy level. It doesn't want to be there. It wants to lower its energy level so it can just hang around. And so if there's an ammonia in the area, it's going to be more than happy to do a transfer. It's going to kick off that phosphate that's keeping it up at that high energy level because of that extra electron. And it's going to bond with the ammonia and get rid of one of the hydrogens, and that's going to bring it down to a low energy level. That's a stable molecule. And so by doing that, the atoms have just done it out of energy considerations. How can I get to the lowest energy level that I can be at? But for our purposes, we've just made a molecule. We've made glutamine, one of our amino acids that the body needs. And so now this becomes the nitty-gritty of why ATP is the energy molecule. It pushes other molecules up into a higher energy state, and it forces when you add a phosphate to a molecule, you call it phosphorylation. So it phosphorylates molecules, pushing them up into a higher energy state, making them unstable. And if there's any other molecule in the area that can possibly bond with, that to get rid of that high energy phosphate, it's going to do so. They're going to have a transfer reaction. It's going to get rid of the phosphate, take on some other molecule, and then it immediately falls down into the lower energy state. When it's at the lower energy state, we call it a stable molecule. And of course, glutamine becomes one of our important amino acids that the body is going to use to make proteins, etc. So that is, and all of that has to be done because of the fact that ATP itself is a positive Gibbs, it has a positive Gibbs sign, it has a positive G. So by saying it has a positive G sign means it's unstable. It itself is unstable. So it's trying to get more stability by giving away one of these phosphates. And so this is just, the cycle is just going to keep repeating itself. You have ATP. ATP is unstable because of all those negative electrons, those extra electrons hanging around the phosphate. The best thing it can do is get rid of at least one of them. And so when it gets rid of one of them, it forms a high energy phosphate plus ADP. And then this is just going to keep cycling around. As long as we can get oxygen, etc., into the mitochondria, we can make more ATP. And so that is what we mean by ATP being the energy molecule. So it all comes out of thermodynamics. It all comes out of these endergonic, the consideration of what's an endergonic reaction and what is an exergonic reaction. So at this point, the concept is relatively logical, and so all it requires you is to pay some attention to what the terms are. So you associate the right terms with exergonic, associate the right terms with endergonic, and remember that if something is spontaneous, it's going to have a negative G sign. The ultimate in spontaneity would, of course, be it would be back here I had it, the explosion. This is a highly spontaneous reaction, extremely energetically favorable. And so, but this is what we don't want to happen in the body. And so we're going to have a whole series of complicated chemical reactions so that we never get to the point where we explode. Catabolism, we talked about catabolism being the breaking down of molecules. This is the ultimate end product of an uncontrolled catabolism, where you just have this massive explosion. But everything in our body is going to be controlled by enzymes. You're going to have those multiple pathways, and so we don't explode. Yes?
So if the body didn't function like that and the stuff would, well, if it didn't function like that, it was going haywire, then we would
Yeah, if you had
blow
no,
up like that.
if you had no series, we started out by saying you have a metabolic pathway, A goes to B, B goes to C, with the help of enzymes. If you had no control, you would do this. I actually have that. Let me see if I have it in this chapter or another chapter. Let me just go forward. I can show you what in theory happens. It's in the next chapter, but I'll do it now. Our oxidation of glucose to make ATP is essentially, if it was uncontrolled, we'll do the gummy bear experiment. Looking for gummy bear. So this would be a catabolic reaction with no enzymatic or metabolic pathway control. So here's a gummy bear. Gummy bears are mostly glucose. And it's going to oxidize glucose, which is what we do in the cells. Of course, we have to watch the commercial first.
Means satisfaction.
So that's you oxidizing glucose Well, they fudge it a little bit, they put a chemical in there to make it, the reaction go longer. But essentially, this will burn, because when we get into the cellular respiration chapter, in order to oxidize glucose, now what they're doing is comparing which has more energy to it, glucose or NMX. And so what's your conclusion? There's the data. What gives you more energy? Looks like the gummy bear had a longer lasting big explosion. So the glucose, of course, is your energy, your input, your carb, and you eat carbohydrates to sugar. Your green starch, it breaks down to glucose. You're breathing in oxygen, and you're oxidizing the glucose. This is what would happen if it's not a biological system. But we have enzymes, we have pathways, we have metabolic pathways, and we don't do this. This is essentially what this does. And so this is going to just keep going. This is the gummy bear experiment was a small version of the explosion that I can't find right now. But, when you take gasoline and you light a fire, you're oxidizing the hydrogens that are in the gasoline, and that's when an explosion occurs. So the principles are the same, but because it's in a living organism, what happens is different. Okay, so there we are. So that's why, hopefully, we know why we need ATP. We are increasing the energy level of a molecule by raising, by phosphorylating it. And the molecule then goes into a higher energy state. It then increases the probability that it's going to react with another molecule because it will go down preferably into a lower energy state. So it's trading one bad for something else that it thinks is better. And it all has to do with energy considerations. Okay, so we're back to our enzymes. And the fact that we can't make a reaction go by increasing heat, otherwise we'll destroy everything that's in the body. We'll denature our own proteins, which in fact are enzymes. So we have to have reactions go at some constant level that is our body temperature. So this is where the enzymes come in. So what we're getting into now is what actually do we mean when we say that an enzyme is a catalyst and increases the rate of reaction. So here's the basic situation for enzymes. Enzyme is protein. Proteins have to be in a certain shape. We talked in the chemistry, we talked about the primary structure and the secondary structure and the tertiary structure. So enzymes are usually in tertiary structures, so they're usually like a ball. And that ball wrapped around polypeptides has a particular shape. That shape will be where something binds to. And so the area where something binds to is called the active site. So the active site is on the enzyme. The thing that binds to the enzyme, whatever it is, gets a name. It's generically called a substrate. So the substrate can be some of the sugar, it could be another protein. We don't care at this point. And so and this is the whole point we did the joke of the lab. When we said by boiling the enzyme we denatured it, or by boiling protein we denatured it, what you do when you denature is you unfold the polypeptide so that the active site is destroyed. And when the active site is destroyed because the enzyme has unraveled, then the substrate cannot bind to it anymore. And therefore the enzyme becomes useless. So these are the terminologies of enzymes. You need a substrate, a lock and key fit essentially. You need a substrate to bind to specifically the area on the enzyme that has a complementary fit with the substrate called the active site. So here's an example. Enzymes are proteins we've mentioned before. They usually end ASE. So if you see a molecule that ends in ASE, you're pretty sure that that's an enzyme. And so here is a sucrose molecule. Sucrose is table sugar. And so table sugar is made up of two sugar monomers. One is a glucose molecule and one is a fructose molecule. And so the enzyme here, called conveniently sucrase, is going to break the bond between those two monomers, between that disaccharide. So right now, sucrose is a disaccharide. All of this should be reviewed from the previous chapters that we talked about. This is a hydrolysis reaction, because in order to break that bond, we need water. And so we're going to split the water molecule into H and OH. That's not going to happen by itself. And so we're going to take that sucrase. You can imagine here that this enzyme would be sucrase. This would be sucrose. And the enzyme will allow the molecule to be split into the two monomers. And so enzymes, in this example, the enzyme is breaking up a molecule by hydrolysis. But in the body, and other enzymes can go the other way. They can be forming dehydration synthesis molecules that put monomers together into polymers. So this is when we say that it's a catalyst, that it increases the rate of reaction, this is the nitty-gritty of what actually is happening. The way you would describe this, the role of the enzyme is to decrease the activation energy. Every chemical reaction needs some level of energy to allow it to go from reactant side to product side. If you have an enzyme available, you will need a lower level of energy. And what that essentially means is if you wanted to make that sucrose hydrolyze into two monomers of sugar in a laboratory, you'd have to do the gummy bear experiment. You'd have to combine it with oxygen and then turn on that Bunsen burner or throw in a match. The heat of the flame would be your activation energy. That heat level is too high for our bodies, and so the enzymes are there to allow that same reaction to go, to oxidize, for example, glucose into hydrogen and electrons, etc., within our own body temperature. And so the energy that you need to make a reaction go from the reactant side to the product side is called EA. EA stands for the energy of activation. And then what the enzyme is doing is lowering the energy of activation. And so this is the amount of energy that you would need without the enzyme. Now you have the enzyme, and so you need much less energy. So when we talk about it being a catalyst, we want to be at the reason why it's a catalyst. It decreases the energy, the needed energy of activation to make a reaction go from the reactant side to the product side. Yep.
This might seem like a weird question, but if you had a lighter and the gummy bear would start blowing up or not?
Would the gummy bear blow? Well, it did blow up.
Yeah, but
I won't say it blew up, it oxidized.
if I had a gummy
Oxidized
bear and
by
started
it.
like burning it, would it do that or no? If I had a gummy bear and started like burning it, holding it to a flame, would
Well,
it start?
if you went home and took a gummy bear and put it in a test tube and took your lighter, it probably would not be as dramatic because in fact they added some other accelerant in there to make it really flare on the video. But in theory, yes, this is what would happen. So when we get into the cellular respiration chapter, we say that you, as a biological organism, are oxidizing glucose. You are not oxidizing glucose in the same way that the gummy bear is being oxidized. The gummy bear experiment is an example of the oxidation of glucose, but the outcome is very different. That was an explosion. That gummy bear went from an ordered substance, a gummy bear, into a pile of ash. So that was going from an ordered state to a disordered state. When you oxidize glucose, you're going to make ATP. And so all of that is because it's happening within a biological system with the help of enzymes, with the help of other ATP molecules, within a mitochondria, which is an ordered organelle. that becomes the difference between life and non-life. We have the capability to maintain that order. So this is where we are in terms of the definition of what an enzyme is. Yep.
Is substrates with reactant?
The substrate is the, well, the substrate would be more equivalent to the reactant. Yeah, it's the thing that's going to bind to the enzyme to allow it to become the product, yes. So we hear the example, the sucrose would be the substrate. It binds to the enzyme at the active site, and now it becomes the product of the two monomers. So this is the polymer. This is actually a disaccharide, so this is all the review of the chemistry that we already went over. Sucrose is a disaccharide, meaning it has two sugar molecules linked together in a covalent bond, and with the help of the enzyme, it's going to turn into a monomer. Okay. Now, so this becomes the subject matter of the next laboratory we're doing, where we're talking about enzymes and the things that affect enzymatic reactions. Every enzyme works in an optimal condition. If the enzyme is not working in an optimal condition, then it's going to be denatured. And so the question that we have in the upcoming lab is what are the optimal conditions for a particular enzyme? And use one enzyme and then look at what happens to that enzyme when it goes away from its optimal condition. So one optimal condition is temperature. Every enzyme is going to work at some particular temperature, and if you're talking about a biological system like a human, our normal body temperature is 37 degrees centigrade, which is 98.6 degrees Fahrenheit, and so that is the optimal temperature for all the enzymes that are at in our body. For other animals, it may be different because their body temperatures are different. So that becomes the reason if people have a fever, if they're sick and they get a fever, if the fever gets too high, they die. And the bottom line of why you die when you have a fever that's too high is it denatures all the enzymes in your body. And for a human, it's been estimated that when the so-called core body temperature gets to about 106 or 107, that cannot sustain life, because at that point, any enzyme that's in your body will be denatured. And as soon as the enzyme becomes denatured, all the chemical reactions stop, and you're no more. Yep.
Is being hot the same as like dehydrated? Maybe the same thing happen?
Well, I mean, we talked at the very beginning of the semester, we talked about homeostasis and adaptations. You're going to have adaptations to try to keep that core body temperature from getting that hot. And so the sweating and the vasodilation, opening up the blood vessels so the water can move into the periphery, the sweat glands, those are all ways to keep the body from getting there. And so what people die in deserts, though, I think Death Valley in the United States is one of the hottest places on earth. I think the highest recorded temperature was over 135 degrees in 1 year. And so what happens there is even you can be sweating, but if you're stuck in the desert, you probably are going to boil the water. And so the whole idea of going back to evaporative cooling, the whole reason why you can sweat and get cool is because the water that's in your blood is absorbing the heat and the hydrogen bonds, and then as they leave the sweat glands, they're turning into a gas, and the hydrogen bonds are breaking and carrying the heat away. If you're stuck in that 135-degree desert and run out of water, you're not going to be able to engage in evaporative cooling. So, it will get, your core body temperature will get up to that level where it denatures protein. That's how people die. And so it has to do with, if you had water, maybe you'd survive, because you could keep making the blood volume have enough to be able to trap the heat. And so here is, now this is for a human, the example we're giving for a human, and they're sticking in here. This is one of our thermophiles. If you remember, we've talked a few times sporadically about those three domains. One of the domains being the archaea, and by definition, archaea are extremophiles. They live in extremes of places of the earth. And so they were just fairly recently discovered, meaning maybe 30 years ago. And the first place they were discovered was deep in the oceans, in those canyons that go down 5-6 miles under the ocean floor. And people were astonished to find that in those so-called hydrothermal vents, where you actually have the lava of the core of the earth coming up into those canyons, where the temperature could be 200-300 degrees Fahrenheit, they found bacteria that were thriving there. And so this was that most recent addition to the taxonomy, the archaea, the extremophiles. And so they have obviously developed an exception to the rule. They must have developed enzymes that actually have an optimal temperature at very high. We're used to thinking about us, and so for a human, the optimal temperature for all our enzymes would be body temperature, which is 37 degrees. And so one of the experiments that we're doing in the lab is just subject that enzyme. We're going to give you an enzyme that comes from plants. It has an optimal temperature, it has an optimal pH, and we're going to ask you to put it in cold and see what happens to the reaction that you're measuring. You can predict, slow it down. Put it in boiling water, see what happens to the reaction that we're giving you. Obviously, it should denature the enzyme, so it all relates to the various stages that enzyme can withstand. The other optimal consideration is every enzyme works at an optimal pH. And so here is the rate of reaction. So obviously, the higher you are up on the y-axis, the greater the reaction. And so this is pepsin. This is an enzyme that comes from the stomach. The stomach releases what to digest proteins? What's coming out of the stomach? Acid, right? Hydrochloric acid, at usually a pH of 2. And so pepsin's optimal pH is actually 2. If you were in the intestine, which is after the stomach, there you have different enzymes that are breaking down the food you eat, and their optimal pH is 8. If you're in the mouth, the pH of your saliva is almost neutral, so what would that be? About 7. And so you have enzymes that are secreted from the glands in your salivary glands to begin the digestion of starches, etc. And so they have another optimal pH, about 7. And so here what it's showing you is exactly what you should predict. As you go away from the optimal pH, you get less and less reaction. And so we were boiling the enzyme, we would see the rate of reaction go down to nothing. If we were cooling, if we were not cooling it, if we were putting it, if the optimal pH is 2, if we're putting it at 8, we should denature it. So pH changes can denature enzymes too, not only temperature differences. So anything that destroys the function of an enzyme is denaturing the enzyme. And extremes of pH can denature also. Yep.
So if you denature it with this can't make it blow, all right?
No, it's just going to not function. There's not going to be any visible sign. Your visible in lab, when we do the enzyme lab, your visible sign of reaction not working is that you're not going to get. We're doing a colorimetric reaction where we're going to give you a molecule that comes from a plant, and in the presence of oxygen and the enzyme that we're going to give you, or that is in the plant, it will change into another molecule that changes color. So the color change becomes your visible indication that you have gotten a reaction. So if you change the pH away from the optimal, it will just not give you a reaction. The color will stay the original color of the reaction. So your indication here is not whether it blows up or not, but whether you see a color change. The enzyme that we're going to give you is coming from I think a potato or some vegetable. It's a food product. And so what would you think the optimal pH for that enzyme would be? Food, vegetables, potatoes are grown where? In the soil. So a wild guess, what's the pH of most soil? No clue? Nobody's ever grown a plant in their whole life? demonstration of the optimal conditions that every enzyme needs, with every enzyme having a different optimal condition. If you talk about a human, the temperature will be the same. The pH, you can see here, the pH may be very different. 7 in the mouth, 2 in the stomach, 8 in the intestine. And so the point is, if the enzyme has been shaped for that particular organ, it's going to, in the stomach, it's going to be able to withstand a pH of 2 and not denature. On the other hand, a pH of 7 would denature it. So those are the considerations. And here's exactly what denaturing is. You are unfolding the enzyme. That's why we spend time talking about the structure of protein. When you make the protein, it's in the primary structure. It's a railroad car. It's polypeptide amino acids strung out like railroad cars on a track, bound together by covalent bonds called peptide bonds. And then, as it goes into the endoplasmic reticulum and the Golgi apparatus, it begins to spontaneously fold, depending on what the particular amino acid sequence was. That's why the genes are so important. I mean, all of this is coming back to roots. This is all material that you should have learned. The genes specify the messenger RNA, specifies the protein. So the sequence of the amino acids is what's determining the shape, because they may be positive charges, negative charges. So that sequence is going to determine the shape of the active site. So when we denature it by boiling it or putting it into a pH that's not optimal, it's going to unfold. And when it unfolds, you no longer, this may have been, we can take this as an example, maybe just this area, this shape, exactly here, might have been the active site for some enzyme. And now it's gone. And so when you denature something, you're unfolding it and you're destroying the active site. If you do that, then the substrate can't bind to it, and then nothing works. And then we're back to the whole body having a core body temperature of 107, all the enzymes that denature, so you're not going to live very long. Okay, and so this is what we're going to be doing in the lab. We're going to be giving you a substrate called catechol. These are ordinarily found in plants. I can give you the example. You've seen it. You just didn't know you were seeing it. Here's what happens to a banana. When you buy them in a store, they're nice and yellow. You bring them home, you leave them out for a while. You can slow down the browning effect by putting it in the refrigerator, but pretty soon it's going to turn brown. And so this is called enzymatic browning. It has a name. This is a video. The food industry spends millions of dollars trying to slow this process down because people don't particularly want to eat brown food. They don't want to eat apples that are turned brown. And so the browning effect is due to this chemical reaction. In the food, you have the substrate called catechol. Here's the shape of it. It's an organic molecule, carbon and hydrogen ring with 2 hydroxyl functional groups. You don't have to go crazy copying it, this is in your lab manual. In the presence of oxygen and in the presence of this particular enzyme called catechol oxidase, which is also in the plant, it will turn into another molecule. It will turn into benzoquinone and water. When notice that there's a difference in the shape. What it's done is it's lost 2 of its hydrogens, and now you have something that looks like this. When the molecule rearranges the shape in the presence of that enzyme, catechol oxidase, it turns from colorless to brown. And so the brown color becomes your indication that you have gotten a reaction with the help of the enzyme. And so if you boil the enzyme, it won't turn brown, it will stay colorless. If you put the enzyme, which works best at about pH 7, and you put it in pH 2 solution, you will denature the enzyme, it won't turn brown, it will stay color. So these are known as colorimetric assays. And so the ability to see the color change is your key that you know the enzyme is working. You could be a chemist and assay industry uses this all the time. They pay lots of money to scientists to try to figure out how to slow down this reaction so that people can buy food or have it stay on the shelves longer and not turn brown, because when it turns brown, they have to throw the food out, so they lose millions of dollars every year, if not billions of dollars. So they work hard and furious trying to figure out how to slow down this reaction. Okay, so the rate of the reaction is going to be, you're looking at enzyme kinetics, how fast the reaction goes from the reactant side to the product side. Okay, that's our